Yeah. Let's see if ModularDiscriminant is available in Discord. Let's see if ModularDiscriminant is on Discord. Hi. Hi. Welcome back, guys. Okay. I am very tired, so let's listen to a math lecture by ModularDiscriminant. Nothing better than to fry your brain more after frying your brain. What am I saying? What was I saying? I forgot what I was saying. Hello. We have ModularDiscriminant on Discord, who made 6 clocks, but like, yeah, very hard clocks. Math major, and I believe they can explain a bit about the 2 clocks and teach me. So, yeah, how should we do this? What do you think about my what do you think about me solving L math is math clock? Do you think I did good?
Really impressive.
Thank you.
Totally didn't think about you explaining all this graduate level math stuff, so I really appreciate it. Yeah. I really respect you. So are you okay? I should ask you, are you okay?
Yeah, I am okay. I'm fine. I am very very healthy. Very mentally healthy.
Yeah. So, okay, thank you again for calling me. I'm now okay. I should share my screen.
Right. Let's listen to ModularDiscriminant's solution to this math clock. And after that, yeah. Maybe after that we are gonna do Pinkish's clock as the final one. And finally I'll be free. Maybe I'll be free from all the clocks. Yeah. So, wait. Okay, this is 12 o'clock. Wait a minute. Are you talking right now? Because if you are talking, I cannot hear you. I think, yeah, I cannot hear you right now. Maybe. Oh yeah, now I can hear.
Are you hear me?
Yeah, I can hear you right now.
Oh, thank you.
Learning about the final 2 math clocks. Bam. Okay. Let's see. Right. This is 12 o'clock? By the way, are you speaking right now? Because you might be muted again.
Um,
Oh, yeah, I can hear you right now.
I'm speaking. Okay,
Oh.
can you hear? Okay.
Yeah.
Okay, so how much do you...
Wait, I think your mic cuts off when you when you go to this screen because I cannot hear you anymore. So I think it's...
Sorry, yeah.
Oh,
What should I do?
okay, maybe... What? Maybe... Actually, are you only on... a pad? Yeah, you do not have a PC right now, right?
Yeah, I'm
okay.
on the bed. What should I do then?
Okay, I don't know why it doesn't work. Someone on chat. You got a... Wait, so you also got an ad? How? I mean, ads give me money, so thank you for watching ads. But like I will turn off ads now. Bam. Not right now. I cannot hear you right now. So, I think maybe...
Oh my god.
I will just ask you questions on... And maybe you will have to... just talk me through it. Or maybe just... if while I write this, maybe you can tell me when I'm wrong.
Okay.
Honestly, with L Math's clock, I did like do most of them. I think this one is the only one I didn't do at all. The 4 o'clock one.
It's basically just easy ones. So the 2026 means dihedral group, as you pointed out, and R just means that the rotation element in that group. So,
Oh, so because it's dihedral, it always has... If you do this, you always get 2. Is that it?
Yeah, right. It's always 2 since rotations make a cyclic subgroup of it, and index is 2, right?
Right. Honestly, I do not exactly know why it would be 2. I cannot give you the full explanation. So, if your screen share worked, then maybe I could learn more about that. But I cannot hear you again, so I think it actually could just be a problem.
Can I make some small screen? Okay. I'm trying about the dual screen.
Dual screen?
Can you hear me?
Yes, I can hear you right now.
Okay, what can you see my screen?
Yeah, I can see your notes there. Right.
Okay.
I guess I'll do this.
Probably okay.
Right.
Okay.
Now it works.
That's fortunate. Okay. Dihedral group just is defined as a group presentation where this one means rotation and this one is reflection, and so basically there are 2 possible conventions for dihedral groups. One is 2n and the other one is the index is n and its order is 2n. It doesn't really matter anyways. So we have this is identity, and what was it? It was R inverse. Okay.
Is rotation, reflection.
Yeah. I think S comes from symmetry, but anyways.
Right.
Symmetry.
Rotation.
Yeah.
Reflection or symmetry.
Yeah. 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 So what these equations mean is that if you have a polygon sorry.
Oh, that has to be n, right?
N.
Because we already had 2n there.
Yeah.
Okay.
For n equals 5, we have pentagon, for example, in 3 dimensions, and what we are considering is the rotational symmetry group of pentagon in R3.
R3, okay.
Yeah, that's because if we only consider rotational symmetries, the pentagons in R2 would become cyclic group, right?
Right.
Yeah. So kind of rotational symmetry group becomes cyclic, and if you consider rotations and reflections symmetry group, it becomes dihedral group.
Right.
C5. Yeah, and it is the same thing as 3-dimensional rotations. Okay.
So yeah. Again, I will explain it for the 4 people in the chat. And you can tell me if I have it wrong. So if you rotate a pentagon in 2 dimensions, like if you rotate it 1/5 of a cycle, then it like looks just like itself. And that's kind of what it means to be a cyclic group like C5. It has rotational symmetry like 5 times. If you rotate 5 times, it returns back to the original position. And then if you have a pentagon in 3D space, then you can also rotate the pentagon like just like in 2D, and you'll get to the original position after 5 times. But you can also reflect the pentagon like that. Yeah, what you just drew, and then the pentagon looks like this, looks same again. So in 3D, you can rotate the pentagon, but also flip the pentagon to make it look just the same. So is it called D5 then? Shouldn't it be called D10 then?
Oh my god. So I'm confusing about notation since I usually denote D5.
Oh, right.
Thank you for a correction. Okay. So these elements are the generators of this dihedral group, and this just means that you get the original direction if you rotate it 5 times. This just means that if you flip it 2 times, it would be the original position. And this operation means that if you flip the pentagon first and then rotate and then flip again, then it would resulting in the counterclockwise rotation.
Right.
So this is a counterclockwise rotation. That is the definition of dihedral group. And this kind of expression is called group presentation. Presentation. And you can, you usually denote these 2 generators by R and S, and that's what written in the 4 o'clock. So basically, this is the rotational subgroup, and its order is obviously 2, since you have only 2 kind of orientations for the pentagon, namely the front face and the back face. Yeah.
Yep.
And actually, the name dihedral group came from the 3-dimensional rotations in the pentagon. So, for example, if you have
dihedral.
Dihedral. If you have a cube or so-called hexahedron, its rotational symmetry group is called hexahedral group. But I should rather draw an octahedron. Octahedron.
That's an octahedral group, and dihedral group is basically some shape that only has 2 sides, 2 faces.
Yeah.
Right.
So polyhedral groups are just symmetry groups automorphism groups of these polyhedrons, and dihedron here means that it is just a collection of 2 triangles. Yeah.
Right.
So kinda one face is facing upward and the other face is facing out. Yeah, downwards, I guess.
Yep.
You can also view this as a spherical tessellation. In this way, it is more natural to call it dihedron. This is the spherical triangle, and this is another spherical triangle. So this consists of the tessellation with 2 triangles.
Okay, I got that.
Yeah. In this way, we call this group a dihedral group, which is the automorphism group of the dihedron.
Right.
Dihedron. Yeah. That's the explanation for 4 o'clock.
Right. Okay. Thank you. I think then other than that, I did understand the gist of stuff. Obviously, if I wanted to know more about this, I would have to start from basic topology and group theory and slowly build my way up. Right now, I just searched up various terms and just understood what those mean in and not in context, but just in a very narrow sense. So I think that's as much I can learn right now. Yeah, I think.
Yeah, right. So for the singular homology groups, I think you can remind this problem.
Oh, right. I didn't really understand why this was 6 or 8. Was it 8 or what it was?
Yeah. So if you give me 30 minutes, I can tell you why it is. Yeah.
Maybe so. I will have to learn just learn topology. So I'll just have to learn topology, right?
I can give you some intuitions, I guess.
Right. Okay.
I won't delve into it very deeply, but I just wanna explain. Yeah, convey the ideas of it.
Right.
Okay, then I'll tell you what this strange symbol means. Homology groups. So homology is a thing you want to study to classify topological spaces.
Classify topological spaces.
Yeah. So topological space was, I didn't actually tell you, but it is just a shape. But it can be more bizarre than the one from the last time. Topological manifolds are locally Euclidean, but general spaces can have different structures. Yeah, so think of it as just a shapes like spheres or torus or planes or something.
Right.
And what homology groups tells you is that, yeah, so-called number of holes. Holes. But in a very rigorous mathematical sense, not not very rough way. Indeed, it allows you to detect 0-dimensional and 1-dimensional and 2-dimensional holes separately. And after you learn about the homology groups, you'll be able to tell the number of 1-dimensional and 2-dimensional holes. So this one is spheres, and this one are torus topologically.
Yep.
And the reason you get 1313 is that the 1-dimensional and 2-dimensional holes number of the holes is 202021111. So yeah.
Okay.
We should delve into some calculations to see that. Unfortunately, understanding singular homology groups requires some work.
Okay.
Yeah, so
Singular.
you looked up everything. Yeah, everything like simplicial and singular and simplexes like that. How should I? Like singular and simplexes are the continuous maps from simplex to the topology space, but this is too pedantic and too boring. We throw away this thing.
Okay.
What we're gonna do is some more engaging combinatorial calculation using the simplicial homology groups.
Combinatorial calculation. Okay.
Simplicial homology groups. So basically what you're trying to do is to approximate a manifold using some triangles and tetrahedrons, so that you can only consider it using the triangles. If you do this enoughly, then you get a sphere, and if you do it in some other mesh, you will get a torus and so on. Yeah.
Okay.
And we'll develop a combinatorial tool which is called simplicial homology groups to detect the number of holes.
Okay. How would we?
Okay. Simplicial homology. So let's think about a simplicial complex. I need to recall the memory. So if you have a triangle, we will consider some kind of sum of triangles. The reason we are doing this is it will be clear at the end. Let's label these vertices. Sum of triangles or line segments we first think about the boundaries of the simplices. For example, this is 1-dimensional simplex. This is 0-dimensional simplex. This is 1-dimensional simplex. This is 2-dimensional simplex.
Okay.
Yeah, and what you're gonna make is to define some boundary maps, which
Okay.
will lower its dimension by 1. Okay. For the one-dimensional simplex, we will okay. I'm sorry about a bit unprepared. We will first think of n chains.
Right.
Okay. The formal
N-chain.
sum of n simplices. So basically, what we are doing is just placing several triangles next to each other, and some of them can have some different. Some of them can have intersecting vertices, and also there can be some negative triangles, and yeah, these are the formal sum of triangles. 4, 5, 6, 7, 8, 9, 10. To consider this formal sum is, we will need some of these machineries later. Since to define this boundary map, we need to consider the whole space of chains. 1 chains. We first consider a triangle whose vertices are 1, 2, 3, and define the boundary map as follows. We'll get some 3 sum of these boundary segments. That they're ordered.
Okay.
I should really mention about orders. Yeah.
But wait. So this is all prerequisite for just understanding what holes mean, right? This is just all going back to combinatorial calculation with simplicial homology groups. And that's so by the way, I didn't think I understood what you mean by simplicial complex and where the mesh of triangles came from. So is simplicial homology groups, is that just making stuff with triangles? Is that just similar to making stuff with triangles? Is it just simplicial homology group what it's called?
So simplicial homology groups are hard to define right now. We will need some. We need to build some machineries like this boundary map, and we need to think about the kernels and images and like that.
I saw the I saw the formula that HK is kernel divided by image, like it looks like that. I saw that. And the kernel K, that's like, and I saw that that's like a K cycle. And the image is just like the boundary. So cycle is when a cycle is a chain that when you take the boundary of that chain, it becomes 0.
Right. Whose boundary is 0? Yeah, right.
Boundary is literally just like, the image of the boundary, like, function.
That's right.
Boundary of something. So the only thing I'm not understanding here is k-chain. So n-chain. We went to n-chains, which are formal sum of n simplices. Okay.
I'm sorry about this messy explanation. I'm a bit unprepared.
Okay. Oh, then how
Let
about this? Can you
yeah
just give me an example
yeah
of a chain that is a
yeah
cycle and like a
yeah yeah
chain that maybe like a boundary of something, what that means in like in examples,
yeah
maybe?
yeah.
Yeah.
Okay. Example is really good way to explain. So indeed, you need to think about oriented simplices, which will be denoted like
Okay.
uh,
Right.
this
Basically, we
the
just have
order pair of vertices.
triangles and yep, the points
Yeah,
we
yeah, yeah,
put some kind of order to points. We just name them 1, 2, 3, right?
yeah,
Uh-huh.
yeah, yeah. So this cyclic permutation of this points ordering is not matter, but if it is reversed, it becomes a negative of itself.
Uh-huh.
And this is the orientation of simplex orient. And if we have two simplices with some orientation, we have an n chain, two chain.
Mm-hmm.
This is the example of two chain.
Okay.
Yeah, this is just the formal sum. This is not simplifiable, but we just write it as plus.
Right.
And what is a cycle? So basically, if you have something like this, something like the faces of a tetrahedron.
Uh-huh. 4. So four of them?
Yeah. There are 4 triangles here.
Okay.
I think I should write it like this way. 4, 1, 3, maybe 1, 4, 2. Am I writing correctly?
4, 1, 3. Like, okay, I guess the order could be wrong here, but
Yeah.
anyway, 2, 3, 4.
Yeah.
Yeah. 4, 3, 2.
Yeah. So this is the boundary of some 3 simplex. 1, 2, 3, 4.
Yeah.
1, 2, 3, 4.
So it's a chain. Basically, they are triangles bundled up together, and they happen to be enclosing like a boundary of a 3D shape in this case. So in this case, that's what makes it a cycle. And it's called 2-cycle because it's made of triangles, which are 2 simplices. Triangles like these. And
Yeah.
yeah. Yep.
I really should have explained about simplicial complex. I'm sorry about this. So 2-cycle. So for the easier example, we have some the formal sum of 3 line segments. Yeah. In this example, you can see why it is called the boundary of 2 simplex. And in this example, we also can see that the sum of boundaries of each line segment would be 0. That's the crucial point. Wow, how can we calculate this boundary of a line segment? It is just the subtraction of these 2 vertices, because it is ordered, kind of.
Yep. Okay,
should
I
write it
understood
this
that.
way? Yeah. So it basically becomes 0 if you calculate everything.
Yeah.
So it is.
That's a cycle.
Yeah.
Yep.
That's a cycle. Yeah. And what things become strange is that your entire space is not an Rn. It is not Rn.
The entire space.
The entire. Yeah. For the entire space, we call. I mean, we should introduce simplicial complex. I remember now. It is something that you get by adjoining arbitrary simplices among the vertices. So here you can see 10 vertices, and every possible edges here are also contained here. Edges. And also there are triangles. I will remove this. Triangles, and yeah, there are 4 triangles here.
Yeah.
And the last one is the entire tetrahedron. Yeah. So how can we write down this kind of
So what we have here, right now is a simplicial complex. That's a simplicial complex. Okay.
Yeah. We define this thing to model the topological spaces.
Okay.
Model some shapes we know, and in this case, vertices are just one. The simplices with one vertex.
Though.
And
one. Yeah. Edges. Right.
Yeah, edges.
All the edges. All the.
And triangular.
Yeah.
Bases. Yeah. In this way, you can define it rigorously.
Yeah.
And we need to consider the cycles in these simplicial complexes. Simplicial complex.
Cycles in the simplicial complex.
Yeah. You can
like the triangle made of lines, or
yeah. You're only allowed to use these existing lines. You are not allowed to use others. 1, 6, 7, 2, 8. So, for example, you can make one cycle using 1, 6, 6, 7, 7, 1. And it is a cycle since its boundary becomes 0.
Yeah.
And it is not a one boundary.
It is not a one boundary?
Yeah.
One boundary
means that it is a boundary of some two simplex.
Okay, but in this case, the simplicial complex doesn't contain the 1, 6, 7 triangle?
Yeah, right.
Okay.
That's basically how this simplicial homology captures the number of holes. So if the simplicial complex do not contain this filling triangle, you can count this number of cycles, which are not boundaries, to capture the number of holes.
Okay.
1 cycles, and which are not boundaries. Boundaries. Yeah, so in this example, all these triangles are field in this tetrahedron, and others do not allow any cycles here. So we have only one possible one cycle here. It's not a boundary. How should I write it? Yeah, is considered a hole. 1D hole. But in this kind of terminologies, we will often count some duplicate holes. So for example, if you make a simplicial complex using 4 vertices and 5 lines, you can see that this simplicial, this one cycle is not a boundary. Is not a boundary. And also this one cycle is not a boundary.
Yeah. So this time it has 2 holes, 1D holes? Or is it it's 2 1D holes.
Yeah, but also we can find this kind of cycle.
Right.
Yeah.
Wait, the lines are backward though, but maybe that doesn't matter? Okay.
Actually, we are we need to make these lines order perfectly, so I subtracted this one from this one.
Oh, right. Subtracting, okay.
Yeah. So this is also not a boundary, which can be considered as a hole.
Okay.
But in that case, we cannot actually capture the correct number of holes. Yeah, so we should introduce some kind of machineries like abelian groups to understand the full linearly independent number of holes. Yeah, so basically third one is a subtraction of first one and second one, therefore it does not count as a new hole. We only will consider the holes that are independent linearly. Is not a new hole.
Okay.
Yeah, that means I didn't actually explain about the weight of the formal sum, but anyways, these triangles would form the quotient groups generator, and we have whole bunch of infinite number of possible cycles, which is generated by these 2 triangles.
In actual like space with infinitely many triangles, right? Yeah.
Yeah. The coefficient can be the integers here. So this triangle corresponds to this.
Oh, right. Yep. Okay.
Yeah.
Okay.
Yeah, in this way, we really needed to think about the formal sums, and we call this structure as Z2. That is the first simplicial homology group of the simplicial complex, like this one. Yeah, so we are counting the linearly independent number of holes. That was the whole point. And you will write down the result as an abelian group. If you understand this, I guess you can understand this kind of things, I guess. Do you understand about this simplicial homology thing?
That's different. Wait. What you just told me is all about simplicial homology, right? So yeah. Okay.
Okay, sorry about my terrible explanation. What we should do here is to make
just holes, number of holes. I learned what the number of holes mean. I learned what the number of holes mean.
Yeah, so if we make some topological space using the triangles, then we can calculate its number of holes. Triangles. For example, the sphere can be modeled using this kind of 4 triangles. I mean, yeah, this one is in backward. Yeah.
Okay. Wait.
Yeah.
So we make topological space using triangles in 2D surface turns into triangles. And
yeah.
So when we do this, that's the simplicial complex. So where is the 1D hole? Where is the 1D hole? Where's the 2D hole? Where's the 2D hole?
Okay. I didn't explain about 2D holes.
Oh, I guess I know. It's just because the inside of the sphere is empty, right? Because the inside of the sphere is not contained in the space. So these 2D triangles form a cycle, but not around any actual thing. But the inside is empty, so it's not actually a boundary of anything. So 2 cycle, like divided by 2 boundary, there's one 2-dimensional hole. Okay.
Yeah. We have Z1 for the second homology group of the spheres. You learned everything about yesterday. It was so amazing.
Empty inside. So
and for the torus, I think we can also model this torus using triangle. So this embedding version of torus is really kind of hard to imagine if we make triangles inside it. Yeah. It is not even easy to draw this. So we'll not use this, but we'll rather use the kind of simpler version of this torus. So in this version, we can just divide it into 2 triangular pieces. And actually the vertices are the same. So
because it's repeating, right? Everything merges into one.
But
so how is it even called then? These are triangles, but all 3 points are the same point. Is it just called 1, 1, 1?
I think I was lied to you. We cannot make this kind of triangles. We should really subdivide it to don't make the vertices collide into many pieces. How should I calculate this one?
Okay, maybe if you cannot think about it right away, I'll just search up on it later, maybe. I think.
Okay, so
I think maybe the answer is that when you okay, let's try applying what I just learned to the torus and see if anything I say makes sense. Okay. So this is torus. I'm gonna think of the middle hole as a triangle, and whatever happens outside, I don't know. Maybe there are just faces like these, and somehow they are all connected. Why did I do this? Bam, 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 bam. Somehow it all connects somehow. This part is empty. So obviously there's one 2D hole because the whole thing encompasses some inside of this donut, but the inside of the donut is not actually filled. So there's a one 2D hole. I can see that there's one 1D hole here if I like make this triangle be the hole, then like maybe this like this is a triangle but it doesn't encompass anything. This is not filled. It's a hole there. So that's one 1D hole. 1D hole. But is there another maybe it's because the outside maybe the outside of everything somehow
actually I think you can find it. Just be a little bit more creative.
Okay. So okay, I'm in a donut. There's this part is empty. I need to find two sort of like shapes that don't enclose anything. But they have to be linearly independent. So of course I cannot just pick the same thing twice. So we already have one hole there. Maybe it's this. I think maybe another hole might be this because that's a shape. Because like it's weird to see here, but maybe on a sphere, whatever line you draw, you can fill it up like this, and that becomes a surface on the sphere. So it's technically kind of like a connected surface. But here, if you try to color this shape in, you cannot color it. It doesn't. You have to color the whole thing, and it doesn't divide the torus into anything. So this is not actually a shape that contains anything in the donut. So maybe that's the second hole.
Yeah, congratulations.
Yay!
Yay! So, I'm writing in my screen.
Okay.
Okay. We have these two kind of linearly independent holes, which corresponds to the two possible essential curves in this surface.
Mm-hmm. Ah, right. Okay.
Yeah. So I think we can just forget about triangulation, and we can just find some closed curves which are linearly independent.
Right.
Yeah, in this way you can see why this is plausible to have two different curves. For example, if you have this kind of curve, then can you see why this is a sum of these two given curves?
Yeah, it's just like I don't know the direction, but it's like blue plus 2 times red or something. Something like that. Yeah, direction. Yeah.
Yeah, I think you're right. Blue. Yeah, that's right. We have to add this given curves to make it. Its gradient is like 2, so yeah, maybe this way. It goes this horizontal direction 1 time, and it goes to this vertical direction 2 times.
Yep.
So it consists of the 1 horizontal and 2 vertical components. In this way, you can analyze every kind of closed curves in torus. Like, yeah, it can be really messy, but it is always a sum of these 2 basic curves.
Yep.
Yeah, that's why we have torus homological group is these 2.
Okay.
This is the number of 1D holes.
Number
and
1D
it is
holes.
called Betti number.
Betti number.
Yeah, named after Enrico Betti. And basically what we are doing here is to calculate the Betti numbers in this problem. It is called B subscript this dimension.
Okay.
So yeah, we have all Betti numbers here, and typically 0-dimensional holes are not as considered as holes, so we add them up to get 8.
Right.
Yay.
Thank you.
Thank you.
Okay.
You understand everything.
Nice.
This one just means that, yeah, as someone pointed out, this just means that the symmetric group and its order is 2. It is 6. I don't know about any critical wordplay.
Oh no, the 8 one is chess. Yeah. So 10 one, they commented that it should be changed, and they just removed remove that puzzle. So yeah, everything else solved.
Yeah. I actually seen this problem before.
Oh yeah, I saw your comment too. I tried to find it in the textbook, and yeah, I kind of get what it means.
Okay. This just means that the meaning of it is the number of algebraic integers inside this field is more than this made by polynomial on alpha, like this. And this example is indeed very famous, called Dedekin's example.
Dedekin's example. I think your voice cut out because you switched to this tab, maybe.
Okay. It cut out again. Okay. So I'll just mention that this example is some kind of weird examples in number theory. Since this number field is not generated by a single element inside this ring. Do you know what an algebraic ring of integers is?
Algebraic ring of integers.
I'm sorry, ring of algebraic integers
is what we have defined addition and multiplication.
Yeah.
And addition
Yeah.
works pretty well. Multiplication,
Yeah.
not so well. No commutative thing or inverse.
Yeah.
Yeah,
Yeah.
that's the ring. And the distributive thing.
Yeah. Right. So ring of algebraic integers, 대수적 정수한, is something we research in the number theory. And basically you can think about these kind of examples. So suppose you have Qi,
Okay.
which is the set of elements of the form rational number times I plus rational number.
Yeah.
And you want to find some algebraic integers inside it. So what is algebraic integers? Do you know?
Algebraic integers is every that like when it satisfies polynomial equation for coefficients that are integers.
Yeah. Almost right. X equals. So if you have some coefficients that are all integers, and it has a solution as a given number, this number is called algebraic number, not integer. 대수적 수라고 부르고요. And if you have these coefficients, and furthermore, the leading coefficient is 1, then it is called algebraic integer.
Really? Okay. Okay.
Yeah.
Right.
So you can think of it in this way. The rational numbers are, of course, algebraic, but they can be defined as a solution of this degree 1 equation of the coefficients. And when we make integers from this equation, we just assume that the leading coefficient is 1.
Okay.
Then we get some numbers that are closed under addition, negation, and multiplication.
Right.
But not division.
Right. Okay, now I understand.
Yeah, so yeah. If we assume that the leading coefficient is 1, the division breaks down here. So what you wanna do is that to find some numbers inside it, such that there is some integers satisfying this equation.
Okay. Right.
Can you find out?
What? Find out what?
What is the general form of algebraic integers inside Qi?
Here isn't it? Wait. Algebraic integers. I feel like it's just a plus bi where a and b are integers.
Yeah, right.
Yeah.
Yeah, so your intuition is indeed correct here. Everything of the form a plus bi, I mean integer plus the integer I, is the algebraic integers here, and they are all algebraic integers. What am I writing?
Right.
But you should be careful about the intuition.
Yeah, because it just the coefficients are integers, but like nothing is said about the solutions actually.
Yeah. This intuition can indeed break down if you consider other rings like square root of 5. which are indeed constructible in PowerPoint in Q. We will denote the set of algebraic integers inside this field as O subscript Q root 5.
Okay.
Yeah, so can you find out in this case?
Algebraic integers are... So... Let's see. X squared plus... If there are integers... And, like, it has to be inside Q root 5 anyway, right?
Yeah.
Maybe it also allows fifths. Maybe integer over 5?
Yeah,
No,
that's a really good intuition.
It almost... I'm not sure.
Okay. This is really some kind of not easy problem, right? To find every possible ways to make algebraic integers is not a simple problem. You can always have these z coefficient ones, but also you have this one.
Oh.
The golden ratio.
Right.
Yeah. Everyone loves this constant, so the golden ratio is inside this ring of algebraic integers, but there can be no more denominators greater than 2.
Right.
Yeah, they will all break down, even if it is 5. Therefore, this ring of integers is generated by the elements square root of 5 and also this one, but it can be simplified. Yeah, since you can make this one using the golden ratio.
Right.
That's what makes this calculation really hard.
Right. And this is where Dedekin's example comes in.
Yeah.
Showing that it's not that intuitive. The solution is not always that intuitive.
Yeah. If you adjoint some element, which is an algebraic number, we call this Q alpha a number field.
Yep.
Since it is usually researched in number theory. And for every number field, its ring of algebraic integers is corresponding. And in Dedekin's example, it is not really possible to make this ring using 1 generators. We need 2 generators. I guess this one.
Right.
Yeah. So it cannot generate this one since there is 1/2 here, the other way around. Showing this property is not that easy. I learned it in my last semester's course, but I can't explain it. And yeah. Yeah. This kind of this kind of ring of algebraic integers is called non-monogenic since it is not generated by 1 element. And you can search it in LMFDB.
Right.
this.
Okay.
So yeah, that is the problem that was already. I mean, that was mint. Yeah.
Right. Thank you for the explanation.
Yeah.
Right. I guess that's where we have to end. I think
Okay.
that is where we have to end.
Okay. I think you understood this.
Yeah. Whoa, thank you for writing down the page numbers there. Right.
For this one, I actually also studied about this combinatorial game theory thing.
Right.
Yeah, it is really some new subject for me. I refer to this interesting book,
Winning Ways.
Winning Ways.
Yep. I heard that's the most oldest. I heard that it's the oldest and maybe not the best one to learn from because it's like there are more like newer textbooks nowadays, but yeah, I heard that it's a good book.
I didn't know about that. It can be old book, right?
Yeah, maybe like I've heard that some of the notation used here are not really used anymore. Maybe. Yeah.
Oh, maybe you're right, I guess. Okay. I just looked up this book since I watched this interesting video.
Oh, is it Hackenbush? Yep. I watched that yesterday too. Yeah. Hackenbush.
Yeah.
The Hackenbush video. Amazing.
Okay, so I think you learned almost everything. You know what domineering, right?
Yep.
About domineering, I calculated all the positions. Where is it? Okay. So when you calculate domineering positions, you can remove this tile and remove this tile to get this is 0, 0.
The bottom one is so they are all neutral.
Neutral.
Both of them are they are stars.
Yeah.
And then star plus star is 0. So that's why there are 6 stars there in the diagram. So they add up to 0, and then there's 1 minus 1 remaining.
Yeah. We have this is just a notation for this one.
Oh, right.
I actually don't know how much did you study, so you know star, and how about this one?
Okay, that's I don't remember what it's called, but I just know that there are 2 squares there, so they just cancel out each other. Oh, it's a switch. Right, it's a switch. Oh, I forgot. Yeah, that's a switch. Right.
But I think these squares doesn't cancel out.
Oh, it doesn't cancel out? Switch plus switch.
I'm confused. Maybe it cancel.
Because if there are 2 of those squares, then the first player is gonna lose. Because if one player places on one square, then the other player can place on the other square, and then there's just a forced after 2 moves it just ends. So I believe it's just gonna be 0 if you add them together.
그런가? Is it 0? I thought it.
I think it just results. Maybe if you try to actually play it, then the first person always have to lose if you have 2 of those squares, isn't it? I think so.
Yeah, you are right. Really? I. Mm, mm. But isn't it something confusing position? I'm confusing right now.
Wait.
I'm adding this manually right now.
Right. So yeah.
Yeah.
2-0. What even is that? 2-0? How do you even write 2-0? 2-0?
2-0. Our first solo. I'm confusing right now.
Yeah.
Do you know about this notation?
No, I only wrote down the ones that are like that ones that I need for the clock here. But anyway.
Okay.
I guess I'll just explain the puzzles that I managed to solve. So I'll just open up my screen here and yeah. So they said that you have to change this one. Here we have up, which is 0 bar star, and star is 0 bar 0. By the way, negative half is negative 1 bar 0, and negative 1 is nothing bar 0. So if you make all of this, you get 0 bar star, which is gonna look like this. And then we have a big bar, and then we have negative 1 and 0, which is negative 1 is this. And then we have 0 again, which is this. And then the number of vertical bars here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 o'clock. And then here we have denominator of. This is the nim value of, and I guess this is subtraction. Subtraction means a game where you are allowed to take, by the way, this is just 2 and 3. That's from other puzzles. So subtraction here, it means a game where there are a bunch of stuff on the board, and you can either take 2 away or 3 away at a time. That's what this 2 and 3 does. And the person who cannot take any further loses. So what is the nim value of subtraction 2, 3? To get the nim value, we need to calculate the MEX minimum. The first number that doesn't appear in a set. This MEX means the first number that doesn't appear in a set. So it works like this. G of Q, that's a nim value, that's this, is equal to MEX of G. In this case, we have 2 and 3, so MEX of G, Q minus 2, and G, Q minus 3. Now, how do we actually calculate this? This is how we start. So this is what we do. We have Q, and then we have GQ. Every time, we start by... Okay, let's write down all these numbers first. 5, 6, 7, 8, 9, and so on. And what we're gonna do is first we write... if there are 0 stuff here, I mean, I don't have to explain this one. There's 0 here. And starting from here, we're going to look at 2 cells before and 3 cells before. There's nothing here, so ignore that. We're going to look at 2 cells before and 3 cells before. And then find the minimum number that is not included in those 2 numbers. So here, you see 0 is here. So the minimum number that is not included here is 1. Now we get to 3. We look at spaces 2 before and 3 before. They are both 0. The minimum number not included in those is 1. Now we get to 4. We look at 2 spaces below, 2 spaces ago, 3 spaces ago. We got 0 and 1. So the minimum number we don't see here is 2. We get to 5. Look at this. 1 and 1. The minimum number we don't see here is actually 0. We don't see 0 here. Yeah, the minimum number, by the way, minimum number as in minimum non-negative integer. So 6. Here we see 2 and 1, so we don't see 0. For 7, we see 0 and 2, so we don't see 1. For 8, we see 0 and 0, so we are not seeing 1. And then it continues. And by the way, you will notice this thing repeats itself, because once we get to 2 zeros, then it's the same thing as this. So this is just gonna continue being 0, 0, 1, 1, 2, 0, 0, 1, 1, 2, so on. And now, if we look here, this thing is 0, 0, 1, 1, 2, so on, so on. This is 3. It says, interpret this number in base 3. So it's like we are trying to calculate 0.011200112 something something. And then the coolest part is this can be calculated just like with just just simple math, and it ends up being, actually, did I even start from 0, 1, 1, 2? I'm not sure. I think it ends up being like 21 over 121. This number ends up being 21 over 121. The denominator of that is 11. I mean, 121, and the square root of that is 11, so that's why this is 11 o'clock. Okay, so those are the few I've calculated. And I think, yeah, this one, I don't know how it makes sense, because we've got, so this is 3 times 2, this is 6. This is minus 7 minus 1, which is 6 and minus 6. So this is a switch, plus minus 6. And I get what this puzzle is about. It's going to be like plus minus 6, and then this is going to be 6. So it's going to be 6 plus minus 6 is 12 or 0. I think that's going to be the thing here. But like here, I don't know how this makes sense, because E plus F, this is going to be, this is like 11, and the right is a really big number. And whenever we get something like this, I think you take 1 more than this. So this just results in 12. And here, this results in 1 and x over 8. And I think the intended solution is to is for this to be 2. But like I don't know how this can be 2, so that's the problem. I don't know how 1 slash x over 8 can be 2, because x is here also, and I don't think like this makes sense as a 2. Maybe I'm wrong. Yep, so that's where I was stumped in that puzzle. This one we had ordinal sum, and the thing is, ordinal sum of A, and this is minus 1 and 1 over 2. So what is 1 colon minus 3 over 2? Ordinal sum, you are supposed to calculate like, it's hard, but I think this ends up being something like this and this, I think. Because negative 3 over 2 is equal to minus 2 bar minus 1. So how you do is you first take the left of this, which is 0, and then you take this together with the left of this, which is that, and to the right, you either I don't know, you take the right of this, which is just nothing, or you take this with the right of this, which is this, and this ends up being, this is 1/4, this is 1/2, so this ends up being 1/4 and 1/2, which is 3/8. And this is weird because h is then, the d is 4. 4 divided by 3/8 is not 8. So I don't know what this is supposed to be either. Maybe this is supposed to be C, then it will make sense. Yeah. So I didn't get this one too.
I think the notation 3.5 is, I guess, 3 plus a half. Maybe?
It's a 3 plus a half. So it's minus maybe this.
Yeah, I think that's the notation, but I also got the wrong answer with that calculation.
Yeah, I think I also did that too, and that also gave me a wrong answer. Negative 7 over 2 is gonna be negative 4 bar negative 3. So this is gonna be, you put the left of this, which is 0, and then 1 colon negative 4, or right of this is just nothing, and 1 colon negative 3, and you get this. This one is like 1/16th, I think. This one is gonna be 1/8. So we have 1/16th and 1/8 like this, and that's gonna be 3 over 32. Bam. Is that what you got? I think, yeah.
Yeah, right.
So, yeah, it's wrong either way in that case.
Yeah.
I didn't get this one too. Did you get this one? By any chance?
The wedge thing?
Yeah.
I think that means the minimum of the two operands.
Oh, it's the minimum? Right.
I just searched it up, and internet said the meet sign means the minimum of two numbers sometimes.
But then...
Yeah, I got 3 minimum 5, so I got 3 indeed.
Okay. Meet. Yeah. I got meet too. It means greatest lower bound.
Yeah, right.
Yeah, greatest lower bound of 3 and 5. I mean, it just cannot be 7. It just cannot be 7. 7 is even greater than 3 and 5. It's not possible.
I don't know about this one too. Yeah.
Yeah. So lots of things I don't know about. Okay. Anything to add there? Maybe something you got?
Yeah. Firstly, I think I have some fancy way to calculate the ordinal sum.
Oh, right.
Can you see my screen?
Yeah.
Okay, so you know about Hackenbush? How much do you know about?
I saw that one video.
Okay. I also saw that video. And Hackenbush positions are like these red and blue lines. And if you have this kind of long straight Hackenbush position, how can you calculate its value? So the Winning Ways book taught me.
Oh yeah, this is.
It can. Yeah.
Yep.
Do you know way?
Just one. Yeah. You go up. You do the divide by half thing. Yeah. Keep doing that and do that. Yep.
Yeah.
And basically, ordinal sum is just putting the right thing on top of the left thing. So.
Oh yeah, right.
Yeah, that's how it works.
Yeah, that was the thing I tried to explain. So, there are two ways to evaluate this tower of edges. First one is adding this kind of sum, positive and negative way. And the second one is to write down the binary expansion.
Yep.
They taught me blue then red is a decimal point, and this is 1, this is 1, this is 1. If you have red, then it would be 0.
Right.
And you need to add the last one.
Wow.
So it is 11.1111, which is equal to
3 and 15/16.
Yeah, thank you. So this is the possible two ways of evaluating a Bush position.
Right.
And if you have this ordinal sum, you can use this method to calculate its value.
Okay.
3.5. And you can put this thing on the top of the blue stock to get this one.
Right.
This is the decimal point. This is 0.0011.
Mm-hmm.
So
add another one at the end, right?
Yeah.
Okay.
That's important. We get this value.
Right.
Yeah, that is for the simple, sometimes simple calculation of them.
Right.
Okay. Yeah, and domineering one, you were right indeed. I got where I got it wrong. So basically, the games have several different representations.
Yep.
And for 0, we have the simplest one, but there are plenty of other representations.
Right.
And it turns out that you can simplify this to this. Yeah, I think.
Right.
Yeah, these are called reversible moves, I guess.
Oh, right. Reversible moves. You just ignore all of them.
Yeah. Yeah, you need to replace GL to GRL and so on. But I'm not really used to these calculations. But maybe, you were indeed right. This is equal to 0.
Right.
Okay. Domineering one was correct, and I also got the same problem with you here.
Yeah, B equals B. They actually confirmed it in chat. They said maybe it was a mistake. Maybe it was just B equals B, and then we were supposed to get B from somewhere else. I don't know where, but maybe.
Okay. But for other problems, it would be a really complicated equation to solve.
Yep.
Yeah. And you explained this very, very greatly. Do you know this one?
Not yet. I didn't get it.
Okay. But I think you know the Cole game and the Snort game.
Yeah. Maybe I just have to actually do the calculations and it will be correct.
Yeah, then it's just a matter of notations.
Right.
So in the Winning Ways book, they indeed use this notation.
Okay.
I think I can show you the book.
Right.
What page was? Oh my god! It was 147. Okay. So the black big dot means that it is a position usable by blue, and white big dot is something possible for red ones.
Right.
And small dot is the one for both players.
Oh, it's only usable by blue, it's only usable by red. Okay.
Yeah.
Right, now I get it.
Yeah. They use this strange symbol to describe that no one can use. So these are just deletable in the games. Yeah.
Okay.
And in this way, you can just evaluate these snort positions, and there's the answer sheet.
Right. So I can just look at that
There's the
and
answer sheet.
yeah, that's the plus minus 2, 2 or 0. 2 or
Yeah.
0? Wait, oh no, just 2 bar 0. Okay.
Yeah, 2 bar 0.
Yeah.
And
if you add them
Um,
together,
I-
I don't know. I'll have to calculate this, but yeah, certainly calculatable.
yeah.
Okay.
Maybe this one. I calculated everything in my notes, so.
Oh,
Okay.
right. Snort 4
Snort
o'clock.
position.
Uh-huh.
Yeah. So if you calculate this, then
You
yeah,
actually
we will
played the
get
game, played the entire game, right?
yeah,
Uh-huh.
yeah. You have 2 sub games,
Uh-huh.
which evaluates the star and plus minus 1.
Uh-huh.
And these 3 possibilities, 2 and negative 2 dominates, and we get
Plus minus 2.
2.
Okay.
Yeah. And for the code game, I don't really know about the notations
Yeah, me too.
about this one.
I think
Yeah.
I think what you wrote here is correct. Yeah. Blue, and then anyone can place XX, maybe? Or maybe nobody can place?
Yeah. In the winning ways book, the point that everyone can play is denoted as a small dot.
Right. But
And-
here it's
and-
just non-existent, and maybe it's just
Yeah,
X,
maybe it's no one can playable,
uh-huh.
but then it becomes this two.
Yeah. Then that's
two-
just
yeah,
that.
that's just one. I don't know how to interpret. So in my calculations, yeah.
Yeah, it's okay. So it didn't become 4. Okay.
Yeah.
All right.
This is indeed called a hot position, something that is not resolved to a number, kind of.
Right.
And there is a whole bunch of theory of hot games, which is thermostat and thermographs and so on.
Okay.
So this is the thermograph of this deep position.
Aha. Right. Amazing.
Don't really grasp the theory, but I just calculated this graph.
Right.
So it is not a number actually.
Not a number. NaN.
Yeah.
I believe they were in chat chat like an hour ago, and I believe they are gonna like comment about what was wrong, maybe in our calculations or maybe maybe a mistake in the clock. Yeah, I guess they will like leave a comment or something. Yep. So.
Okay.
Right. Anyways.
For some positions with
Yeah.
left moves are greater than right moves, you call these positions not a number, and like these positions are considered to be hot indeed.
Right.
I think we I can maybe explain about this. Do you want to hear?
No, I get what I get what it means by hot.
Okay.
I get how it breaks down into plus and minus and stuff. Yeah.
Okay. Okay. I really don't know about this.
Yeah, 5 o'clock, I tried to find a few different sources on what kinds of like 3-player game theory.
Yeah.
But then even when I tried to plug it in, like it just didn't work because I don't know anything about GL, right? GL is 3, but then I don't know anything else about GL, and I'm supposed to calculate GL plus GM plus GR. So there's gonna be some kind of mysterious relationship between them that I don't know about that somehow helps me solve this. And then like I don't know. Yeah.
Okay, so I also don't know about 3-player games and anything. But I think you can grasp this concept of GL and GR.
Yeah. Oh, I know what it means. I know what GL, GM, GR
Okay.
means. Yeah. So there is one G.
Okay.
Yeah. Left side is L. Middle side is gonna be M.
Yeah.
There are gonna be 3 players. Right side is gonna be R. Yeah. Yeah. I know what
Yeah,
that means. Right.
Okay. So I think you know everything, but why do you not grasp this one?
Oh no. I was just a little bit confused about it at first, but I get it's just 1 plus minus 1. No, it's just 1 plus minus 1, right?
Yeah. Okay.
Yeah.
So you studied everything, like serial numbers and so on.
Yep.
Okay. I also got this equation is something wrong.
Yep.
And this is
like 7 o'clock doesn't seem to work. 8 o'clock doesn't seem to work. 9 o'clock they told me that there is like they told me to change the rules a bit and then it works, but I will have to do it at a later time. So
I actually found that if you change, what am I doing? If you change this F to, if change this to T, then this becomes 9 indeed.
Oh, if that change, okay. That's not what they told me to do, but yeah, I guess that also solves the problem, right? Because the top left one is star, right? The top left part, T blank F, toad blank frog, that part becomes a star.
Right. I did a whole bunch of calculations to, got this stuff.
Yeah. Like that's a star, I think.
Right.
Yep.
I got star. And for this
TT.F. was the hardest one. Yeah.
Yeah. I calculated using this sub problem.
Wow. I tried to get a code from the internet that calculates this in, but then the C code just didn't work, and I just didn't know how to debug it. So I just yeah. Anyway, it was okay. So it is 3/2, right? It's 3/2.
Yeah. I did every manual calculation. We get 3/2.
Yeah. So if we don't change anything, we should get like 8 plus star, I think. Yeah, 8 plus star.
Right.
8 plus star.
I got
and
8 plus star, so
you can change that star into a 1. Right.
Yeah.
Yep.
That would fix the problem in normal play way. Okay.
Right.
So calculation was really funny here. Okay. Number of
we just did that one. We just did 11 o'clock.
Yeah.
Yep. 12 o'clock.
I also don't know what.
I don't know what that means.
Yeah, this value is 2.
Yeah. If x is 12, right? So that just doesn't work, I think. Yeah, but that solves the entire clock. We just went through the entire clock. Not all, but yeah, whatever.
Yeah.
Good enough for me.
Yeah.
Okay, well. Thank you so much for doing that. I never even requested you to do this, but yet, like, you took time to learn this today. I mean, I also took time to learn this yesterday and the day before, but
yeah. I think you really did some hard jobs, so I respect you. Really.
Thank you.
Hooray!
Great. Okay.
We are done now?
We are done. Wow, thank you, Number Basher, so much for that. I will, I don't know, I'll just do some outro and just celebrate this completion and end the stream. Yeah, so thank you very much for being here. This is ModularDiscriminant, everyone. Thank you.
Thank you for inviting me, and I really worry about your health now.
Right.
So take care of yourself after the stream.
Thank you so much.
Thank you.
Okay, goodbye. Have a nice evening. Bam. Okay. So, right. Does that conclude our journey of math clocks? I think so. I think so. I do not have any more health or mentality left to continue any more clocks. I cannot look at any late submissions. Sorry. But I can end this stream with a bit of piano. Okay, guys. I'm gonna do some improvisation, celebrating the completion of math clocks. If anyone has a note or a chord, send it in the chat. I'll just randomly look at it. I'm setting up my piano. That transgender artist says C major 7 add 13. Wait, let's first change it to go to the piano and turn it on. Reduce the music, stop the music. Change the voice filters. Okay. Yeah, asphalt, right. C7, it's just C7 add 13, okay. So we have C7 add 13. Any more chords or notes? You just type anything from C to B. C sharp, anything to B. Whatever. Hand. Hands are so sweaty because I was wearing this glove for like 4 hours. Okay, something about F sharp, but with C7 add 13, okay. That is C7 add 13. Okay, let's go. Thank you. Thank you. And that concludes the, what do I call it? The judging of the Math Clock Contest 2026. Bam. Right. Thank you, everyone. Thank you, everyone. I will have to, I'm gonna eat so much. I can eat so much right now. I'm starving. I'm starving for approximately 12 hours. Right. No, I had a sandwich. I ate one sandwich. Right. The judging suffering. Thank you. Thank you. Maybe it's a bad idea to play the piano after being battered mentally, because my piano playing isn't there if I in that mental I don't know. Hope it was good. Thank you everyone. Thank you everyone for watching the stream. It's unbelievable that more than 5 people would watch this to the end. It's unbelievable that there are more than 5 people watching. So thank you very much. Right. Thank you. Thank you. Bye bye.